Okay, here we have another session in the IP showcase for NAB 2024, and this is a three-person presentation, so we'll let them juggle their own responsibilities.
It's going to be awkward.
Okay, and you guys are going to have to synchronize yourselves. But the question that they're going to try to answer is whether or not synchronous Ethernet is a must-have or a gimmick for the broadcasting industry. And standing up at the podium right now is Yevgen Kostyukiewicz from the European Broadcasting Union. We also have Nik Kero from Oregano Systems, as well as Thomas Kernan from NVIDIA. So look forward to a very interesting presentation. Take it away, Yevgen.
Yeah, I was tasked with the challenge to make this topic entertaining for you. So we'll do some interactivity. Who knows PTP here as a concept? Okay. Who likes PTP here? Okay. Who knows synchronous Ethernet? Okay. We have some work to do here. Good, good. So hopefully you'll take something from this presentation today, which is a question that we asked ourselves because in the other industries, specifically in the telecom industry, the concept of synchronous Ethernet has been around for a while. And we started thinking, well, is there an application for it? And can we actually use it in a meaningful way and learn from the other industries like IT, like the telecom, for the technologies that we already do quite a lot, right? So IP wasn't done for media, wasn't invented for media, just like PTP wasn't invented and created for media. We are adopting best practices with other technologies, so why not looking at the timing? Simply because today, we are doing fine with PTP for most of our installations, right? So in various papers, in various recommendations, in various requests for comments, you will find different requirements towards the accuracy of your synchronization tolerance between endpoints in about plus minus 500 nanoseconds to 1 microsecond. So for example, if we look at the requirements towards AES11, right? However, if we look deeper into the standards like ST2110, in a synchronous mode that ST2110 operates in, it requires tight synchronization for packet pacing, right? So of course there is a requirements towards frame synchronization, and there will be a certain resolution of that, but also in the packet pacing world, we really look at individual packets as we put them on the wire and as we read them from the wire. And that actually is quite tight, right? So we're in the nanoseconds range. And in most cases, even a plus minus 100 nanoseconds is not enough for that. And that's why we need PTP for that, and that's why we need precise PTP synchronization for that. To add an insult to the injury, we now look at the things like resolutions beyond UHD and white color gamuts, which means more information in a frame, which means more packets on the wire, which means bigger tolerance, finer tolerance of how you put the packets on the wire. And then we add on top the high frame rate, which means more frames with more packets with tighter tolerances. And also applications like virtual productions, you may not think about it, but actually, if you have a skew in the pixel rendering in the GPUs, the whole wall, the whole virtual production wall will look off. So there is a synchronization in the GPUs, and oftentimes when we build those systems, we don't think about it, and also the requirements towards synchronization in those GPUs. And the last point where we can improve things is the holdover performance, which is actually the most expensive thing to improve in a timing solution, right? So in the NAB conference or around the world in the timing conferences, you may hear about using rubidium oscillators, cesium oscillators, using multiple of those atomic generators in your system, which is nothing wrong with that, but you won't be able to put it in every single device in the chain. So maybe there is a better way to provide this holdover performance. And this is what I'd like our colleagues Nik and Thomas, who are way smarter than me, by the way, so you'll enjoy it much more, to talk about now and tell you about the research that we've done in that area.
Good afternoon. Thank you, Yevgen, for setting the stage. Now let's really jump into why we actually did that. And just when we step one step back, we look at distributed system. That can be a production plant, that can be an all IP studio, that can be a power plant. We need a common notion of frequency and more often than not a common notion of time. That's sort of the basic requirement we have nowadays, and these systems all nowadays use Ethernet as a medium. Any other legacy communication media, they are a thing of the past. There are no field buses, there is no SDI any longer. So with Ethernet being asynchronous, we have to find a way to actually synchronize a network, and that's done packet-based. And PTP has evolved to be the more or less only viable means to do that. So we have Ethernet and PTP, which should do the trick. In a nutshell, PTP, I'm hoping I do not preach too much to the choir. So it's rather simple. It's a bidirectional time transfer. Whenever a device requires time, it establishes a bidirectional time transfer with a reference, with a single reference in a network. And that selection of that reference is done autonomously, part of the standard. That's quite neat. And when we timestamp these messages, that the message is carrying time information, when we timestamp then, and with this time information, the device wanting to synchronize its local clock to the reference is now able to do that. It can calculate the offset and account for the transmission delay. And that's, so we have one reference, we have a active PTP network device, a boundary clock. First of all, these two clocks are synchronized with each other, and in a subsequent stage, the boundary clock transfers time information to all devices attached to it. And now we have all synchronized. And this is done, of course, via message exchange. And we have a frequency required to communicate between if two adjacent nodes want to communicate with each other. They use a common frequency, but within Ethernet, the different frequencies on the different ports are not identical. They are not phase locked. They are roughly the same, but they are not the same. That's important to keep in mind. So for broadcasting, PTP, oops, did I miss? No, that's fine. For broadcasting, we have well-established subset of features within PTP, and it's actually really become indispensable for the all IP studio. So that's just roughly what we require in the broadcasting industry. We have layer 3 communication, and important to know also it's suited for very small networks in the same way as for really a large production plant where you have a large all IP studio. And we can even regenerate legacy video sync signals out of absolute time if you want to run sort of a mixed production. Now, Ethernet is, I mentioned Ethernet is asynchronous. So why do we actually bother about that? It's not completely asynchronous. I mentioned previously, two adjacent nodes have to agree on a common frequency to be able to exchange data. Otherwise, that won't work. And who provides the frequency and who actually uses the frequency, that is established when I actually, when the link is established, that is agreed on between both parties, but the roles are arbitrary. That we have to keep in mind. So there are a lot of advantages. The advantages is that that system imposes no limitations on network topology because every link has its own transmission frequency. And when I change my network topology, that won't affect any other part. When I change a part, that won't affect any other thing. And we can use low quality oscillators. And of course, the downside is we have no common frequency. And every node, when we want to have a common frequency, every node has to regenerate the same frequency from absolute time. And that, of course, as a result, that frequency has limited accuracy. So the frequency, when we really want to adjust, when we want to have a common frequency in our plant, then we have to regenerate it from absolute time information. But that time is not ideal. We have a number of sources contributing to overall noise. We have inaccuracies, which cause that time information we maintain on the follower, which fluctuate. And when I use that fluctuating time information, where we have some certain inaccuracies, use that to generate a frequency, that frequency will wander as well. So, but what if that frequency stability is key to my application? What if I really need a stable frequency? So frequency wander would kill me. Or if I really want to have something which is sub-nanosecond, guaranteed with enough headroom, like a 5G base station, then the only solution, the only viable solution the industry came up with, and I believe it's the right way, is we transport frequency over Ethernet. So we kick out that asynchronous idea again and return to a synchronous Ethernet. We have a strict hierarchy to establish, and that actually has the ITU, the telecom industry, has defined that. There are a number of standards, ITU recommendation, which cover that. And on top of that, also to be more flexible, the ITU has defined a low-level protocol where you can actually transport the information of the quality of the frequency. So when I want to receive, when I want to use that frequency provided by the network, I know about its quality, and I know whether the quality changes, and whether I use it, I stop using it, I can reuse it. So that's the stage of synchronous Ethernet, and now I hand over to Thomas, who will tell you a little bit what we actually measured with and without syncing. Thomas.
Thanks, Nick. So now that we've gone through the technology basis, we're going to look at the actual measurements we performed. Oops. So we built a very simple network, and the design is on the next slide. What we have is a direct connection between a reference, will be common for both setups. We have a grandmaster, which was externally locked, and on the other path, we had a PTP boundary clock in the middle, so a switch. Obviously, all the infrastructure has syncing capabilities. And what did we actually measure? We decided that we wanted to see two important things, which are usually the two references you look at when you're looking at timing information. We wanted the phase offset that was generated between the PTP grandmaster, the reference, and what was measured by the endpoint, the PTP follower. And the other thing we wanted was the actual internal view of the PTP stack on the follower, what it thinks is the data that is used, and how does that compare to the actual external reference, which is the grandmaster. And What did we measure? We wanted to see the effects over a period of time. We arbitrarily took something that was beyond 5 minutes, so it's representative of the failures with the GM conditions. So you'll see we'll run through the different slides with how we did the different failure conditions. Setup is extremely simple. GNSS for the time of day external reference, a Meinberg M3000. We were outputting the reference 1 PPS, which was then fed into the two endpoints. So one of the endpoints actually is running a board with an oven-controlled oscillator, and the other one's running with a temperature-controlled oscillator. One of the connections goes to the switch, and the PPS comes from the same reference to both of the devices. And since the boards that we're using in the endpoints actually allow us to do internal comparison, we don't need an external oscillator for doing the PPS measurements. So we're measuring the difference between the PTP hardware clock that's disciplined by the PTP stack with the reference PPS that was coming through the PPS in of the board itself. Oops. There we go. So first of all, we're looking at the data output from the PTP stack, which in this case is plotted over more than 5,000 seconds. And obviously at the beginning, when we started, there's going to be a control loop that's going to settle. So we've left that in the beginning to show that we haven't done the cutoff. And then we see it's actually very stable, and it's got a peak to peak of about 17 nanoseconds for this. So this is the direct connection between the Grandmaster and the actual endpoint, okay? Just as a reference, this is running over a 1 gig connection. Now, if you look at it from the external point, we're looking at the PPS here, okay? So this is actually not what the PTP stack statistics tell us, it's what's the offset between the Grandmaster, the reference, and the actual PHC, the PTP hardware clock that's been disciplined by the stack. As we can see, reality is actually peak to peak of plus minus 5 nanoseconds, so 10 nanos. And within that range, I mean, it's more in the noise, the fact they've got a little bit of stepping within a couple of nanoseconds, but over a period of 600 seconds, so 10 minutes, this is this is the behavior of a stable system. So again, this is for baselining the infrastructure before we actually do the failures. Now this is the connection with Synchronous. So before we saw it with just PTP running, and now the difference is we have frequency, and we're disciplining it also with frequency, and we can see that if you look at the PPS offset in this case, we have even less of a difference. So we have, peak to peak of about 4 nanos, not even 4 nanos, across the a period of 1,000 seconds. So now you've got all the different baseline configurations, PTP only, PTP with Synchronous, and the measurements from the reference, the stack itself, versus the external reference, i.e. the Grandmaster. So this is where we start doing failures. So on the left, we have a stable system, which is PTP only, and we fail the Grandmaster. So at that point in time, we're free running. Okay, so this is across the direct connection where we're going from the Grandmaster to the PTP follower. We recover, the PTP Grandmaster is now back. So obviously there's going to be a slight undershoot, overshoot because of the PTP stack that's locking again. At that point in time, we're also going to introduce Synchronous. Now get a second failure condition. So PTP is not available anymore. So the Grandmaster doesn't have PTP. But the rest of the graph, where we recover, is actually running in assisted holdover. So it's only frequency. It's via the Synchronous. To make this slightly more clear, we're zooming in on just that last event when we had the failure. And you can see that we have only frequency here that is doing the correction. And then, of course, we have the stack that comes back online when PTP messages come back, and we've got the overshoot, undershoot, and then stabilization. This is with the direct connection model, okay? Now, if we look at this from a PTP stack point of view, same build, Did I go back? Did I go forward? Okay, so then it animates automatically. Fine, no problem. Um, we have the same failure conditions, and in this case, Nick, we have synchy or not synchy? The slides are reversed.
No, that's the same with the Sync.
Oh,
No, that's the same, but from the PTP stack.
sorry, from the PTP stack. I apologize. It's jet lag. I'll claim it's jet lag. So yeah, so this is the case where we're looking at from the PTP stack itself and not from the PPS, which were the previous slides. So again, we've got the failure condition at the beginning. Well, first of all, we acquire lock. That's why you've got the pull-in at the beginning. Then we've got the PTP grandmaster that's failed. Then we have no data from the PTP stack because obviously the PTP stack's not running. So that line is a fictitious line until we recover the PTP stack because the grandmaster is available again. And therefore we correct, we inject synchy. So we've got PTP and synchy. At this point in time, we've got failure of PTP only, and we're doing the assisted holdover. So we have no PTP data. And then we recover the grandmaster, and then we have a slight overshoot undershoot, and we're back to where we were before. Okay, I'm seeing nodding heads. Good. So this is the other scenario. This is the one where we have a boundary clock in the middle, which is obviously synchy aware. And in this case, this is the PPS plot. So same kind of events. We have at the beginning a PTP grandmaster failure, which is PTP only, there is no synchy. Then the second one is the PTP grandmaster we recover. So we've got a slight correction. We inject synchy also. So we've got PTP and synchy running. Then again here, the yellow arrow, we have actually the failure of the PTP stack, synchy only, so frequency. And then we recover with the overshoot undershoot. Well, in this case, only an overshoot. And then we're back into a stable system. So this again is viewed from the PPS perspective. This is the interesting bit. Viewed from the PTP stack point of view, compared to what you saw before, you will notice that I have PTP information all the way through. Why is that? Because when there was the PTP grandmaster failure, the boundary clock took over as the currently best elected master. And therefore, when you look at this data, you see there's a little bit of noise, the red line at the beginning. That's when there was the PTP failure for the grandmaster. And then we recovered and we had the synchy, okay? And the point here is, since we are still locked to a PTP source, because we have the boundary clock, and since we have synchy that is being fed through the system, and we have this assisted holdover on the boundary clock, and also on the endpoint, we have an extremely stable mean of 0.01 nanoseconds over the period of the measurement itself. So once we have a peak-to-peak simply because we've got a pull-in and everything else, but you saw it from the PPS output before, it was extremely, extremely stable. With that, I'm going to hand back to Yevgen.
So logically, what you will say now, gee, Thomas, Nik, Yevgen, your plotting skills are amazing, and they are, but what does that mean in practice for media? Well, we can obviously see that with Syncy, we can, first of all, achieve tighter synchronization between the nodes in the PTP plus Syncy performance, right? So we can go beyond what the pure PTP can offer us for applications that require tighter synchronizations. But I think what is the biggest value here is the last plot that you've seen with a stable PTP performance after the boundary clock that was getting this assisted holdover frequency source via PTP. What does that mean? So imagine you have a spine leaf network, right? And you have boundary clocks all over it. And then suddenly you lose your grandmaster. In a very unlikely case that you lose both grandmasters and you lose your feeder switch, it's like, okay, your system is going free running. the boundary clocks, and that moment, you are at the mercy of the performance, the holdover performance of your boundary clocks, right? So one of the switches will drift away to the right, another switch will drift away to the left, and at the end of the day, you will have a system that just slowly falls apart. In this scenario, where you add sync E to the equation, you can keep the system tightly aligned without changing any sort of quality of the oscillator inside of the switch. Does it come for free? No, because this is a telecom grade equipment. It often is more expensive than what we deploy for media applications with pure PTP. However, this is a thinking point that maybe we need to start talking to our network vendors and say, hey, you know, this, I heard about this technology. Why don't we kick it in? Because nothing changes from the upper layers perspective, right? So it doesn't mean that we are running now synchronous workflows like we did with the ASCBU or MADI or SDI. No, the IP and the Ethernet remains a wild asynchronous workflow as it was. You just throw packets out there and hope that they reach the end. The synchronous part is only at the bottommost layer, the physical layer. And for the applications that run on top, it's completely transparent. They don't see the difference except for the timing performance of the stack that is provided to you by the switch. So no need to change your end equipment, no need to change your sources, your destinations. If your equipment at some point can accept sync key at the reception, great. Your device will also benefit from that independent frequency source. However, the biggest value, in our opinion, is in the last boundary clock that will provide you the assisted holdover to the rest of the network, and it will keep the whole system in line. I'm starting to repeat myself, right? So yes, it is not free. Yes, it is not widely available in media industry. Telecom industry has been doing this forever, right? So we're not reinventing anything. Just once again, just like with PTP, we're just looking at, can we borrow some things to make our world better? And will it work for 2110? Yeah. Will 2110 benefit from it? Yes. Will it benefit IPMX? I would expect a conversation with John, who sees like he's seriously considering what we just said, and I'm looking forward to the conversation that we'll have at the back of the booth. Yeah, so just something for you to think about. We plan to continue looking into it. I shouldn't say anything for the record. I was asked not to commit, but probably you'll hear on this topic a little bit more from us. On that note, thank you very much for your attention. Hope you learned something.
Thank you. Great presentation. Really interesting topic. I want to see if anybody here has any quick questions. Yeah.
So very quickly, the real value in this is if your grandmaster fails. Is that right?
It's a loaded question, right? So if, for example, you have, so yeah, probably yes, because I'm building mentally a diagram and seeing a different, like, will it help if I have, for example, a grandmaster that is connected to a GNSS or any other traceable source, and that traceable source fails? Probably not, because then we are at the mercy of the holdover of the grandmaster, right? So if it drifts, then yes, the whole system will drift away. But if you have a decent grandmaster, which you should, that will mean that the stability of that grandmaster will be propagated down the line much better than if you don't have that mechanism, right? Because you're in that case, your switches, so you need to understand that the error is propagated and multiplied as you go down the chain, right? So your grandmaster's tolerance will increase, but so will the of the boundary clock switches down the line. This is where I'm probably digging a grave here, and I'm, yeah, okay. So if you can preserve that error across the chain, the end result will still be better with this mechanism. Yeah.
further to what Yevgen just said, there is also one advantage. You mentioned the real advantage is when the grandmaster fails. That's correct, but when you look into more detail, the grandmaster may just fail because somebody pulled the plug or the power is gone, but the grandmaster may generate corrupted data, do anything, but has all of a sudden error conditions which are more difficult to detect and to resolve. And so even in that scenario, we have a stable frequency, we have sort of assisted holdover. So we cover our bases far better than with having maybe more grandmasters, which by the way is a good thing.
This is a very good point, because if you have, for example, an event of PTP spoofing or an attack on PTP that disrupts, for example, the software process in the grandmaster, it will not affect the physical layer oscillation synchronization, because it's based on physics, not on the logic. So, for example, if your boundary clock process fails, the frequency recovery would still be there, because it's on a completely different level of operation.
Thank you.
Anybody else? Anybody else? Okay, gentlemen, thank you very much. Very interesting. Take care.